Welcome back to the Math Professors. Today we're going to cover Lagrange multipliers, and I'm going to do this through this example of g of x comma y comma z is equal to x squared minus z squared minus 1 is equal to 0. So what we're looking at here is a hyperbolic cylinder. Now the reason why they call this a hyperbolic cylinder is if I had a cylinder like sliding in the y direction like this, cylinders look like like this. Now this equation would be equal to x squared plus z squared is equal to 1. So if I have x squared minus z squared is equal to 1, we have a hyperbola. So what I want to do is I want to find the values on the g function that are closest to this origin. So what I'm going to do is I'm going to look at a side view of this. So we're going to look straight down the y. So the y is going to be coming right out at us. So graphing that hyperbola, really I'm just going to graph these lines right here, or these curves right here, are going to look something like this. So in order to find the values that on the blue that are closest to the origin, we can kind of tell that they're going to be right here and right here. So the way we do this is we think about some kind of expanding bubble or sphere in this case. But when we're looking at a side view, it's going to look like a circle. But let's just look at the two-dimensional side view of this. So as the circle gets bigger and bigger and bigger and so on, what's going to happen is it's going to eventually run right into that hyperbola. So I really just want to look at this part here. So when this sphere essentially runs into the hyperbola, we can see that these right here are going to be the closest points. And what we notice is when this happens that the normal of the sphere is going to look like this, and the normal of the hyperbola is going to look like this. Now, what I can tell is that the normals are parallel. I know they're opposite directions, but they're parallel. And the same thing will happen to the other side. The normal over here will look like so, and the normal on the sphere is going to look like this. So if I put this into the 3 dimensions, what we can see is something that looks like this. So as the sphere grows, you can see it's going to hit this backside, this front side of the g function. So what Lagrange multipliers do is they really take advantage of the fact that these normals are parallel. So what we know if we want to find the normals, they're related to the gradient. So what we do is we set up the system of equations that says the gradient of of f is parallel to the gradient of g. So what I'm going to need is I'm going to need that f function. Well, that f function happens to be this sphere. So we know that f of x comma y comma z is going to be this growing sphere centered at the origin. So x squared plus y squared plus z squared. Now it's growing, that's why this is not equal to a constant. This is really an expanding sphere. So I really just have to solve this system of equations right here. So the gradient of f is going to be the partial derivative, so this is going to be equal to 2xi, comma 2yj, comma 2zk. I like to write them in this form, it's a little easier. And then this is going to be parallel to the gradient of g. Now we'll talk about this later in a second here. So this is 2x, comma 0, comma negative 2z. What parallel means is that these vectors being parallel means that there's some constant multiple of each other. Here's an idea. So if I have the vector 1, comma 2, I know that this is going to be parallel to the vector 2, comma 4. The reason why is that this vector times 2 is going to give us this vector. So we can see 1, comma 2 being this, 2, comma 4 being this. Now, if these were both negative, they're just going to be in the, instead of this way, it's going to be this way, essentially. So that's why we're talking about parallel vectors. All right, so we're going to set up the system equation. So I have 2x is going to be equal to lambda times 2x. We're going to have 2y is going to be equal to lambda times 0. And then we're going to have 2z is going to be equal to lambda times negative 2z. So vectors are equal when their components are the same. So what we're going to do is I'm going to solve this. Really, our goal here is we want to plug. We really want to solve using the constraint, And I can't solve the constraint now because it's of two variables. So what I want to do is I want to write z as a function of x, or we can say x as a function of z. So basically I want to write this in terms of x or this in terms of z, and it's kind of our choice. So I'm going to solve this. So 2x is, minus lambda times 2x is going to be equal to 0. So factoring out our 2x, we're going to have 1 minus lambda is equal to 0. And solving this for really lambda is going to give us lambda is equal to 1 or x is equal to 0. So this has two solutions. We have, x is equal to 0 or lambda is equal to 1. Now I know that x is not 0 because it's right here. This thing doesn't even touch x equals 0. It's not a solution. So plugging lambda equals 1 into here, we're going to have 2z is equal to 1 times negative 2z, or 2z is equal to negative 2z. Now, solving this for z, sending the z over, I have 4z is equal to 0, so that means, does that make sense? So that means z is equal to 0. All right, so what now we're going to do is, this now is solved really kind of in terms of x, is really 0 times x. And what I now can do is I can plug this back into here. So plugging it back into the constraint says that x squared minus z squared is minus 1 is equal to 0, but z is equal to 0, so I have x squared is equal to 1, which says that x is equal to plus or minus the square root of 1 or plus or minus 1. So now we have the coordinates x is equal to plus or minus 1, y is equal to y is equal to 0 here as well. So now we have the points negative 1 comma 0 comma 0 and the point positive 1 comma 0 comma 0. And we can see that those 2 points do make sense here. This is going to be x is equal to, this is 1 comma 0 comma 0, and then on the back side we're going to have negative 1 comma 0 comma 0. And those things are going to be closest to the origin. All right, I want to use another example, and then we can get another idea of really what this looks like geometrically. So I'll pause it, I'll set it up. All right, here's my example. So find the greatest and the smallest values of the function f of x comma y, which is equal to x squared plus y squared. Basically, that it takes on this circle x squared minus 2x plus y squared minus 4 is equal to 0. So let me give you some geometry. So in general, what we've done previously is to be able to find your maximum and minimums of a function on a closed interval. So the previous examples that you do in Calc 3 class is you talk about like a closed interval being maybe a triangle or maybe a square. So the way we do this is you find the max and mins on the interior by the partial derivatives equal to 0, and then you also have to test all the edges and also all the endpoints. But what happens if it's not like straight lines, or if it's not like a triangle or a square? What happens if it's a curve? How do you do this? So this being our blanket function, I like to call them blankets. When I look at this, if I want to find the max and mins of this paraboloid right here on this constraint, or really this domain restriction, what we can see is that this is going to intersect this like somewhere like, let's just kind of do my best as far as a picture. So what you're going to get is you're going to get something that looks like this. You're not going to get the entire paraboloid. You get part of it because it's this paraboloid constrained to this domain restriction. So what I want to do is I want to find the maximum and minimums of just this part of that thing. So the way we do this is again with Lagrange multipliers. I know that the gradient of f is going to be parallel to the gradient of g, which basically means that this thing is going to be our g function. This is going to be our g of x comma y comma z. Now, what I try to tell students is, how do you know what the function is and how do you know what the constraint is? Well, the constraint's always going to be equal to some constant. That's why I know that this thing was the constraint, because I have this function equal to 0 or some number. I could say it was equal to 4 if I want. I could say equals 4 by sending the 4 to the other side. So as long as this thing is equal to a constant, we know that this is the constraint and this thing is the function. So the gradient of f, this is going to be 2x comma 2y, and this is going to be parallel to the gradient of g. So the derivative with respect to x is 2x minus 2, and the derivative with respect to y, oh, this is supposed to be 4y, let me put that back, minus 4y is equal to 0. So, and this is going to be 2y minus 4. Okay, so setting up the system of equations, these vectors are equal when their components are equal. So 2x is going to equal lambda times 2x minus 2. And then 2y is going to be equal to lambda times 2y minus 4. Now, since this is a system of equations, it's kind of your choice on how you want to solve this. So I'll take a slightly different method because the functions are slightly more complicated. So what I'm going to do is I'm going to solve this for lambda, I'm going to solve this for lambda, and then I'm going to set the two things equal to each other. Because remember, what we're trying to do is I'm trying to plug maybe y as a function of x. Or you can do x as a function of y. It depends on what you want to solve for. It's your choice here. So let's solve this for lambda. So 2x all over 2x minus 2 is going to be equal to lambda. And then I'm going to have 2y over 2y minus 4 is equal to lambda. So if they're both equal to lambda, then they're both equal to each other. And that will allow me to solve y as a function of x. So over here I have 2x all over 2x minus 2 is going to be equal to 2y all over 2y minus 4. So cross multiplying, we're going to have 4xy minus 8x is going to equal, multiplied over here, we have 4xy minus 4y. So those will cancel. So we're going to have minus 8x is equal to minus 4. So minus 8x is equal to minus 4y, dividing both sides by negative 4. So I'm going to have 2x is equal to y. So there basically what we have is I have y as a function of x, which means I can now plug these things back into the constraints, here and also here. So plug it into the constraint. We have x squared minus 2x plus y squared, so this is 2x squared minus 4 times 2x is equal to 0. And now I can solve this thing for x. And once I know what x is, I can plug it back into here, back sub, define what y is. So we're going to have x squared minus 2x plus 4x squared minus 8x is equal to 0. So we get a quadratic, so 5x squared minus 10x is equal to 0. So factor in the 5x, I get x minus 2. So what I get solutions are x will be 0 and x will be 2. So x will be equal to 0, and then also x will be equal to 2. And then back subbing into here, when x is 0, this is 2 times 0, so y will also be equal to 0. And plugging 2 into here, 2 times 2, I'm going to have y is equal to 4. So we get 2 points. Basically, our critical points are 0, 0, and then 2, 4. All right. So how do we find, or how do we determine what one is the maximum and what one's the minimum? Because I can kind of see it. Like, clearly this point right here is going to be our minimum, and then it looks like 2, 4, so x equals 2, y equals 4. Up here, the way this thing is shaped, it's tilted up. This 2, 4 is going to be our maximum. So the way that's done is, in order to determine what's the maximum of my f function, that's this thing, I'm trying to find what is the maximum of this. I plug those values back into here, and the biggest will be the max and the smallest will be the minimum. So let's test. What is f of 0, 0? Well, this is 0 squared plus 0 squared, which is equal to 0. And then what is f of 2, 4? F of 2, 4 is going to be 2 squared plus 4 squared. So 4 plus 16 is going to be equal to 20. So that means this one is going to be the minimum, and this one's going to be a maximum. So I'll just even say it in point form. X is 0, y is 0, z is 0. And then the absolute max, x was 2, y was 4, and then z is 20. So please consider liking, subscribing, and sharing. Thank you.